So, dear students, in the last lecture we studied turning of a car on a circular path with the help of friction and independently with the help of banking. Now we are studying turning when both friction and banking both are present. So actually this is a practical situation in our real life. We see that when we are turning on a road, definitely friction will also be present and the road will be banked also. So previously what are the formulae we got for turning only with the help of friction? Then Vmax, maximum velocity with which I can turn on a road. So that is given by Vmax is equals to square root of mu s into gr. And for banking angle, we calculated banking angle tan theta is equals to v square by gr. So these are the two equations we got. This is by turning only with the help of friction. And this is the banking angle in which I can move with a velocity of v only with the help of the raising one end of the road, which is called banking of the road. So this is only with the help of banking of roads. Clear? So now we are going to study a practical situation where the car will take turn when both these conditions are present. When friction as well as banking both are present, then let us see how we can solve this problem. So in this condition, again we can have two conditions. So one condition is what is the minimum velocity with which I can take a turn on this road, and second condition is what is the maximum velocity with which I can take a turn on this road. So first let us consider the situation of minimum velocity here. So if velocity is minimum, this car, it will try to come towards the center of the circular path in which it is moving. So this car is moving in this circular path, where the center of this circular path will be somewhere here. So this car tries to come down this inclined surface. Then we can say that friction will develop in opposite direction. So limiting friction will develop in opposite direction because this car tries to come towards the center of this circle, because mg sin theta will be greater than the centripetal force which is created along this inclined plane. So, and if I draw the free body diagram of this one, then I can say that mg weight component, weight is acting downwards, and normal reaction will be acting in this direction. So this normal reaction I can split into two components. So if this is theta, this is also angle theta, then I can call this is n cos theta, then this component will become n sin theta. So these are the two components in which I can split this normal reaction given by the inclined surface on the car. Similarly, this limiting friction also I can split into two components here. So this is angle theta. So if this is the limiting friction, this I can split into FL cos theta, and this I can split into FL sin theta. So these are the different components which we have here. Now if I observe here, n sin theta is towards the center of the circle and FL cos theta is away from the center of the circle. So for a body to move in a circular path, definitely there must be some force which is always acting towards the center of the circle. So definitely I can say that n sin theta must be greater than FL cos theta. Then only there will be some net force which is acting towards the center of the circle. So therefore, how can I write a net force relation? I can write n sin theta minus FL cos theta. This provides centripetal force which is called mv square divided by r. So let it be our equation number 1. Okay. Or instead of FL I can write mu s n also. So let us write that. So n sin theta minus mu s n cos theta is equals to mv square divided by r. So let it be our equation number 1. So after this, if you observe the other free body diagrams here, definitely I can say that this n sin theta is in n cos theta is in upwards direction, and FL sin theta is also in upwards direction, and only force which is acting downwards is mg here. So as this body, it is not moving up the incline, down the incline, it is present here only. It is traveling along this path only. So definitely I can say the vertical forces must be balanced in this condition. So definitely I can say A1 cos theta plus FL sin theta. So these two are balancing the weight of this car, which is called mg. So again I can write n cos theta plus FL can be written as mu Sn sin theta is equal to mg. From this one, if I take n common, then I can write n into cos theta plus mu s sin theta is equal to mg. So let it be our equation number 2. And from equation number 1 also, again I can take n common. So from equation number 1, if I take n common, then I will get n into sin theta minus mu s cos theta is equals to mv square divided by r. So let it be our equation number 3. So if I observe equation number 2 and equation number 3, from here I can get n is equals to mg divided by cos theta plus mu s sin theta. And here also I can get n is equals to mv square divided by sin theta minus mu s cos theta. So therefore equating n value and n value I can write. So mg divided by cos theta plus mu s sin theta is equals to mv square by r into sin theta minus mu s cos theta. So this is how I can get the equation. So cancelling m value and m value, now I can write v is equals to square root of, so this g into r will become gr into, and this I can write it as sin theta minus mu s cos theta divided by this value is cos theta plus mu s sin theta. So this is the minimum velocity I can move on this circular path with the help of both the friction as well as banking angle. So this is the equation which we got. Now we are trying to solve what is the maximum velocity I can move on this circular path with the help of both the friction as well as banking angle. So let the banking angle is theta here. So if velocity is maximum, this car will try to move away from the center of the circle, or it will try to go up this inclined plane. Then friction will start acting in downwards direction. So this should be the direction of limiting friction. So as velocity is maximum, definitely friction developed will be maximum, and maximum limiting friction we call it as limiting friction. So weight of this car is acting downwards. Normal reaction is acting perpendicular to the inclined surface. So this normal reaction I will try to split into two components. So if this angle is theta, definitely this angle also will be theta. So this is n cos theta, and this component will become n sin theta here. So then I can split this friction also into two components here. So how can I split this one into two components? So definitely I can split it like this. So if this is theta, this angle also is theta. So this becomes FL cos theta, and this becomes FL sin theta. So this is how I have split the normal reaction and limiting friction into components. Now if I see the force which is responsible for making this body to move in a circular path. For any body to move in a circular path, definitely centripetal force is required. Now if I see here, n sin theta is acting towards the center of the circle. Center of the circle will be somewhere here. Similarly, this FL cos theta is also acting towards the center of the circle. So definitely I can say n sin theta plus FL cos theta, both of them are responsible for providing centripetal force to this car. So which is given by mv square divided by r. So if I take n sin theta, instead of FL I can write mu s n cos theta is equals to mv square divided by r. Now if I take n common, I can write it as sin theta plus mu s cos theta is equals to mv square divided by r. So let it be our equation number 1. Now if I see the vertical components which are acting, n cos theta is acting upwards, Fl sin theta is acting downwards, mg is also acting downwards. So definitely these vertical forces must be balanced because car is not moving upwards, car is not coming down here. So along the vertical plane it is in rest position. So therefore I can say n cos theta must be equal to Fl sin theta plus mg, because these are the two forces which are acting downwards and n cos theta is acting upwards. So I can write n cos theta is equals to, instead of Fl I can write mu s n sin theta plus mg. So again if I take n common out of these two, then I can write n is equals to mg divided by cos theta minus mu s sin theta. So let it be our equation number 2 here. So if I try to equate these two relations, so here also I got n value is equals to mv square divided by sin theta plus mu s cos theta. Here I got n is equals to mg divided by cos theta minus mu s sin theta. So if I equate these two, then I can write mv square by r into sin theta plus mu s cos theta is equals to, next I write this relation, this equals to mg divided by cos theta minus mu s sin theta. So m gets cancelled, so therefore I can write v is equals to square root of this g and r will become gr into sin theta plus mu s cos theta divided by cos theta minus mu s sin theta. So this is my relation for the maximum velocity with which I can move on a circular path with the help of both banking as well as friction. So if we observe the previous equation, then what was the previous equation we got? V minimum is equals to square root of gr into sin theta minus mu s cos theta divided by cos theta plus mu s sin theta. So if you observe these two equations, one thing we can observe here is, here we got plus and here we got minus, here it is minus and here we got plus. So this is the only difference between maximum velocity and minimum velocity. Now let us see the concept of conical pendulum here. So if a vertical pendulum, if it is rotated in a horizontal circle, then it is called a conical pendulum. So this is a pendulum which can rotate in this circular path, and this is a horizontal circle in which it is rotating, and here a shape of a cone is formed here, so that is why we call it as a conical pendulum. So let mass of this bar be cm, radius of the circular path in which it is traveling, let it be r, and this pendulum is making, let it be an angle theta with respect to vertical, and tension developed in the string, let it be T, and length of this string, let it be L. So these are the assumptions which we are taking here. Now if I draw the free body diagram of this bob of this bob, then mg is acting downwards, tension is acting in this direction. So if this angle is theta, then definitely this angle also will be theta. So therefore this I can split into two components, T cos theta and T sin theta. So this is how I can split them into two components. Now if I see here, this T cos theta is balancing this weight of this bob. So therefore I can write T cos theta is equals to mg. Now if I take this T sin theta, this T sin theta is an unbalanced force. So definitely, and it is acting towards the center of this circle here. So T sin theta must be responsible for providing centripetal force to this bob. So because this bob is traveling in a horizontal circle, definitely somebody should apply the centripetal force. And this T sin theta, as it is acting towards the center of the circle, definitely I can say T sin theta is providing the centripetal force. So if I divide these two relations, then I will get tan theta is equals to V square divided by GR. So if you observe this relation carefully, this was the same relation which we got for banking of roads also. So tan theta is equals to V square divided by GR. So to this angle of the angle in which the bob is present with respect to the vertical, to this angle bob can travel with a linear velocity of V. So that is how we can relate this relation. So therefore V can be written as a square root of GR into tan theta. So this is one more relation which we can write. Now same relation, if I want to write instead of this R, radius of the circular path, I want to represent in terms of length of this pendulum. Then here we can see there is a right angle triangle which is formed. This is the hypotenuse, this is the adjacent side, and this becomes the opposite side. So if I draw this diagram again, then this is how I can draw this diagram. So this is length of the pendulum L, this is angle theta, and this is radius of the circular path. And this hypotenuse I can split into two components, L sin theta, and this becomes L cos theta. So definitely I can say radius of the circular path is nothing but L sin theta here. So if I substitute in this velocity relation, then I can write V is equals to square root of GL sin theta tan theta. So this should be our equation for velocity, linear velocity of the bob, or tangential velocity of the bob in terms of length of the pendulum. So V is equals to square root of GL sin theta into tan theta. Similarly, in the same condition, I can also calculate the tension which has developed in the string also. So if I consider this one as my equation number 1 and this one as my equation number 2, then I will square and add these two relations. Squaring and adding. Why I am squaring and adding these two? Because I don't want these angles in the final relation. So therefore, here it is t square cos square theta, t square sin square theta. If I take t square common, then it is equals to sin square theta plus cos square theta is equals to m square g square plus m square v power 4 divided by r square. And we know sin square theta plus cos square theta value is 1 here. So therefore t square will be equal to, and if I take LCM of these relations, then I will get m square g square r square plus m square v power 4 divided by r square. So therefore t is equals to square root of, and m square is common here. If I take m outside, then it will be m into g square r square plus v power 4 divided by, this is here r square divided by r square. This is our relation. Now if I take r also common, then I can write t is equals to m by r into square root of g square r square plus v power 4. So this is our relation for tension developed in the string. So a body is rotating such that its angular acceleration is varying with respect to time, as alpha is equals to 6t cube plus 8t radians per second square. So find the angular velocity magnitude at t is equals to 4 seconds if it starts from rest. This is the question. So we are supposed to find out angular velocity, and the equation of alpha is given, that is alpha is changing with respect to time according to this given function which is given. So we have a relation that alpha is equals to d omega divided by dt. So which can be written as d omega is equals to alpha dt. Now if you integrate on both sides, then I will get, and what are the limits of integration? He said that initially body is in rest, so angular velocity initially is 0. Final angular velocity only we are supposed to find out. So therefore the upper limit will become omega. And here alpha is changing with respect to time here. So we are integrating this alpha with respect to time. So we have to write the limits of time here. So initially when I started observation, then time should be 0, and finally at t is equals to 4 seconds I am supposed to find out the angular velocity. So therefore my final the upper limit of integration will become 4 here. So therefore I can write down, so here integration and differentiation will get cancelled. So omega, and the limits are from 0 to omega, is equals to integration from 0 to 4. Omega and alpha value is 6t cube plus 8t into dt. So if I apply the limits of integration here I will get omega is equals to, and integration of 6t cube is 6t power 4 divided by 4 plus 8t square by 2, and the limits are applied from 0 to 4 here. So omega is equals to, so if I apply the upper limit and no need of substituting the lower limit because every term will become 0. So upper limit if I substitute, I will get 6 into 4 power 4 divided by 4 plus 8 into 4 square divided by 2. So here I can write it as 6 into 4 cube plus 4 into 4 square. This is the relation I will get. So 4 4s are 16, 16 4s are 64 into 6 plus 64. So if I solve this one, I will get 448 radians per second. This should be the angular velocity after a time interval of 4 seconds. So this is our answer. Let us see the next question. Angular retardation of a body is given by alpha is equals to k into cube root of omega, where k is a constant. So find the time after which body will come to rest if at the time of observation angular velocity was omega naught. So retardation is given here. So angular retardation is given by alpha is equals to, so minus k into cube root of omega. So minus is written because body is retarding actually here. So then we are supposed to find out the time after which this body will come into rest position if at t is equals to 0, that is at the time of observation angular velocity was omega naught. So we know that alpha is equals to d omega divided by dt, and this is equals to minus k into cube root of omega. So therefore I can write d omega divided by, if I take this cube root of omega to this side, then I will get minus k into dt. I am writing this because d omega, if I want to integrate this one with respect to omega, then this d omega and cube root of omega, there should be on the same side. Now this I can write it as d omega divided by omega power 1 by 3 is equals to minus k into dt. Now applying the integrations limits on both sides. So integration of omega power minus 1 by 3 into d omega is equals to integration of minus k into dt. Now let us see here how we can apply the limits here. So initial angular velocity he gave, it is omega naught, and finally body should stop, so final angular velocity should be 0. So and time at the time of observation means time becomes 0, and after how much time it will come to rest, that we are supposed to find out. That I don't know, so let I place that one to be t here. So this is how we place the limits. Okay. Now if I integrate this one, so integration of omega power minus 1 by 3 is omega power minus 1 by 3 plus 1 divided by minus 1 by 3 plus 1, and limits are applied from omega naught and 0. And here I can write, so k is a constant, I can take it outside, minus k if I take outside, then integration of 0 to 2 dt. So here integration, this differentiation gets cancelled. So finally what I will get is omega power 2 by 3 divided by 2 by 3, and limits are applied from omega naught and 0. So this becomes minus k into t. And instead of t I can place small t only. So this is the result which I will get here. So upper limit, if I substitute 0, total value will become 0. So I am substituting the lower limit. So therefore I will get minus omega naught power 2 by 3 divided by 2 by 3 is equals to minus k into t. So minus minus gets cancelled. So finally what I will get here is, so I will get t is equals to 3 by 2 into omega naught power 2 by 3 divided by k. So after this much time, the body is finally going to stop. So this should be the answer to my question. See the next question here. So a wheel is subjected to uniform angular acceleration about its axis. So wheel is accelerating angularly. So from rest in first 4 seconds, it rotated through angle theta 1, and in next 4 seconds, it rotated through angle theta 2. Then we are supposed to find out the ratio of theta 2 divided by theta 1. So this motion is an example of non-uniform circular motion, or you can say it is an uniformly accelerated circular motion. So for uniform motion, we have already studied the equations. For uniform motion, we can write the equation displacement is equals to velocity into time. And analogous equation of this motion in circular motion is theta is equals to omega into t. For non-uniform motion, that is for uniformly accelerated motion, we have different equations. V is equals to u plus at, s is equals to ut plus half at square, v square minus u square is equals to 2as, sn is equals to u plus a into n minus 1 by 2. And the analogous equations of these equations also we have studied in circular motion, which we can write omega is equals to omega naught plus alpha into t, theta is equals to omega naught t plus half alpha t square, and omega square minus omega naught square is equals to 2 alpha theta, and theta in nth second is equals to omega naught plus alpha into n minus 1 by 2. So these equations we can use now in this condition. So this is a uniformly accelerated circular motion, nothing but a non-uniform motion. So definitely one of these equations we can find out here. We can use to solve this problem. So let us see what is the data given here. So it is given that body is starting from rest position. So initial angular velocity is 0. And first 4 seconds, so t1 is equals to 4 seconds, and displacement theta is equals to theta 1. So definitely I can use the relation s is equals to ut plus half at square, and analogous equation of this equation in circular motion is theta is equals to omega naught t plus half alpha into t square. So theta naught value is theta 1 for first interval. So initial angular velocity is 0 plus half into alpha into time taken is 4 seconds 4 square. So theta 1 is equals to half alpha into 16, so which is equals to 8 alpha. So this is my equation number 1. So theta 1 is equals to 8 alpha. This is my equation number 1. Now for second interval, it is given that it is after 4 seconds. So after 4 seconds means for the second interval, definitely omega naught is not equal to 0. So for after 4 seconds, we are supposed to find out what is the final angular velocity we have. So that we can use, we can calculate by using this relation. V is equals to u plus at. So analogous equation of circular motion is omega is equals to omega naught plus alpha into t here. But the problem is alpha value is not given here. So therefore, I will try to solve this problem by considering the total interval of first 4 seconds and next 4 seconds. So if I consider total interval of 8 seconds, then it means that again I am considering from the first interval, from the first conditions where angular velocity was 0. And in total 4 seconds, total angle covered will be theta 1 plus theta 2. So therefore, for total time interval, how I can write the relations? Again, I can use the same relation of s is equals to ut plus half at square. So the analogous equation I can write. Now for calculating for total interval, so therefore I can write displacement is equals to theta 1 plus theta 2 is equals to initial velocity is 0, so plus half alpha into total time taken is now here 4 plus 4, 8 square. So therefore theta 1 plus theta 2 is equals to half alpha into 8 8s are 64. So please, theta 1 plus theta 2 is equals to 32 alpha. So this is my equation number 2. For theta 1 already I got the equation as 8 alpha, so substitute in this relation. So 8 alpha plus theta 2 is equals to 32 alpha. So therefore theta 2 is equals to 24 alpha. So this is my equation number 3 here. So theta 1 is 8 alpha, theta 2 is 24 alpha. I am supposed to find out theta 2 by theta 1. So therefore theta 2 divided by theta 1 is equals to 24 alpha divided by 8 alpha. So alpha gets cancelled. So theta 1 by theta 2 is equals to 3:1. So this should be my answer for this. So let us see this question. So seconds hand in a wall clock is 10 centimeter. Find the magnitude of change in velocity of tip of this seconds hand in 15 seconds. Also find the magnitude of change of average acceleration during this time interval. This we are supposed to find out. So if I consider this as my wall clock, then if I consider its initial position is here and tip of the seconds hand is here, and after 15 seconds it will reach here. This we know already, because in 1 minute it will complete a total 360 degrees. In 15 seconds it will cover quarter of the circle. So when initially seconds hand was here, the velocity of the tip direction was in this direction. So this I can call it as v1 dash. After 15 seconds, the tip velocity will be in this direction, which is called v2 dash. So magnitude of v1 dash should be equal to magnitude of v2 dash. But v1 dash is not equal to v2 dash, because velocity is a vector quantity. If direction changes, definitely you can say velocity no longer is the same. Velocity has changed now. But magnitude, that is the speed of the tip of the seconds hand, it remains constant. So magnitude of velocities remain constant. Now here we are supposed to find out a change in velocity. So if I take initial directions of velocity, then this is v2 dash and this will become v1 dash. But I am supposed to find out a delta v dash, which is called as v2 dash minus v1 dash. So final velocity minus the initial velocity will become the change in velocity. So therefore v2 dash direction I will keep at it as it is. So this is v2 dash, and I will try to write minus v1 dash. So minus v1 dash is just changing the initial direction. So this is minus v1 dash, and if I take the resultant of these two, then this becomes delta v dash. So that is the change in the velocities of initial and final. So as this is a right angled triangle, definitely I can say delta v dash magnitude is equals to square root of v1 square plus v2 square. But the question is how to find out this velocity now. So we have a relation v is equals to omega into r. Okay, so radius is already given. So here length of this hand will be nothing but the radius of the circle in which this tip of the hand is moving. So here r value will become 10 centimeter. Then what about omega? Angular velocity, is it given? Yes, angular velocity is definitely given, because this seconds hands it will complete total 360 degrees of rotation, or it will cover 2 pi radians in a time of 60 seconds. So therefore I can write angular velocity omega is equals to, it covers an angle of 2 pi radians in a time of 60 seconds. So this is equals to pi by 30 radians per second. So therefore speed of this velocity of the tip, or speed of the tip of this seconds hand, can be written as v is equals to omega into r. Omega value is pi by 30 and radius is 10. So this is equals to pi by 3 centimeters per second. So this is the velocity which I got. Now if I am supposed to find out a change in velocity delta v dash, then I can write a square root of pi by 3 whole square plus pi by 3 whole square, because magnitude of velocity remains the same. So therefore, what is the result I am getting finally? So delta V, magnitude of delta V dash, or just I can write delta V is equals to root 2 into pi by 3. So centimeters per second. So this is the change in velocity which I got. Now there is a second question also in the same question. If we want to find out the magnitude of average acceleration in the same time interval. So acceleration, we know it is nothing but change in velocity by time. So therefore acceleration can be written as delta V divided by delta T. So this change in velocity is in a time interval of 15 seconds. So therefore I can write root 2 into pi by 3 divided by 15 seconds is equals to root 2 into pi by 15 3s are 45 centimeters per second square. This is the average tangential acceleration of this